Okay, so we will continue. First, I will rewrite the transfer function for charge pump base. So, content of the lecture. So, we will continue charge pump based PLL, then some non-ideal effects in charge pump based PLL, and then we will start talking about analog PLLs, and then finally lock range and capture range, which were not covered previously. So for charge point based PLL, I correct the transfer function. The C should be there. And phase transfer function, which is same as frequency transfer function. Same denominator. So you just repeat. Okay, just 1 upon C is left. Okay. For lecture 24, yeah, here. So this should be C, and also will have C. So therefore, omega n square is I upon 2 pi C k VCO and 2 zeta omega n I upon 2 pi k VCO into R. Okay, some literature use omega 0 instead of omega n. Therefore, if you see omega 0, it's same as omega n. Because in some literature, again, omega 0 is used for free running frequency of VCO. That's why I didn't use omega 0. And free running frequency of VCO is when input of VCO is 0. Center frequency. Okay, now we will continue. So now in this new, actually, there is a concept, I tell you, you can think about it. See, for example, if you look at low frequencies, and if you look at the main transfer function of this charge pump-based PLL, which has now compensation. This compensation is because of adding resistor R and 1 0. So, of course, this compensation works very well. But if you look at very low frequencies, if you look at this main transfer function, so it is like this when there is no R. And because of this, system was not stable because we had pulse on the j omega axis. And if you look at here also, here because now you have put R, therefore that j omega axis frequencies have gone away. So therefore it seems the system is stable. Now actually what will happen for the loop gain? So in this system. So, and of course, zeta omega n and omega 0 is given, so zeta can be chosen to be enough large, and therefore it will be stable. But actually, if you look at the loop gain, so if you look at loop gain, I draw it again so that this was phi in S. So if you notice at low frequencies, actually effect of R is not considerable. Right? So therefore at low frequencies, actually your loop is like the same as before. At low frequencies. So one may would expect, okay, at low frequencies therefore there will be, system will be unstable. Same as before. Right? Because if you make S large, low frequency, therefore effectively R effect is negligible and therefore it will be unstable at low frequencies. And then this is one thing, and one more thing is about loop gain. Now loop gain will be I upon 2 pi R plus 1 upon SC 2k VCO by S, which is eventually a, by the way, this is called, I tell you one thing that you may see in the literature, so therefore to know what does it mean. So now loop gain is second order, it has a double pole at S equal to 0 and it has 1 0. So because there is a double pole, at s equal to 0, it is called type 2. It's a type 2 system or type 2 PLL because it has. And type 1 is the case when you have one pole at s equal to 0. This is just for the information. Now, how this loop gain will be as a function of omega? So because you have a second order pole at s equal to 0, therefore it will have a slope of minus 40 dB per decay. Right, this is 20 log. And at 0, which is 1 upon RC, slope will reduce to minus 20 dB per decay. The absolute value of a slope will be less. And this is, in fact, unity gain frequency of the loop. And sometimes again for PLL literature, it is called crossover frequency. Because for op-amp, usually we use unity gain. Therefore, this is called unity gain frequency or crossover frequency. So the trade-off which was there was system was not stable, and here now system is stable, and furthermore, because now you get better control on the unity gain crossover frequency, therefore you will be able to get a better speed also. So then this is up to you how to choose this unity gain frequency, because eventually this crossover frequency of loop gain will determine your cutoff frequency of the whole feedback loop, which is the PLL. Eventually, bandwidth of the PLL is determined by the crossover frequency of the loop gain. So it is of the same order. And therefore, this is one of the parameters now for the design. You have 1 degree of freedom. And this helps to have a stable system. But interesting point, if you look, for example, at low frequencies, you have a very high gain. It is clear from this plot. It has a very high gain. And if you look at your phase at very low frequencies, so you have 180 degree over here and 180 degree over here, means that already you have 360 degree phase inside the loop. Therefore, seems loops to be unstable. So eventually, this is one of the good properties of the PLL loop. So it doesn't oscillate really at those frequencies, because what happens is that at very low frequencies, actually your input of the charge pump, or eventually these two phases will be almost equal, so that you don't get any signal. Output of this phase difference eventually module will be 0. So that's why your charge pump doesn't work. Loop settles to a steady state and stays there, ideally. Otherwise, always it's a question, like I have always this question, see, this system at the beginning is unstable and we are trying to make it stable at higher frequencies. So if you remember when I was talking about XOR, I told you there are 2 regions of operation at which one is PLL is stable and one region which is not. But actually that unstable region still is okay. PLL with XOR also works, right? Of course, separate from the problems it has. The point is that even if it is not stable, if you remember, so it will not stay in that unstable state, it will toggle. to some stable region. Or signal actually may finally settle to 0. Here for this type 2 system, eventually it happens. Otherwise, one would expect to have this loop completely unstable. So now, what I'm saying is that, see, I'm looking at phase margin. I say that, see, if you look at your phase margin, phase across the loop, do you agree phase across the loop is 360 degree, 2 pi? And do you agree your gain is above 1? So it is not a stable system. But at the same time, still it works. And I'm saying that the output of phase comparison, phase difference is 0. Therefore, you don't have any signal in there. Yeah, that is captured in this equation. In the sense that in this equation, it says that though you have an input, but your output is 0. Means that your at least error is 0. And therefore, when you have 0, therefore nothing comes to the input of VCO. Means that it's a stable state in the sense that you don't get any signal at the input of phase comparator. Or in fact here at the output of charge pump. I mean in the block diagram at the input of phase difference. You don't get any signal. So you don't have any signal which creates that kind of energy generation inside the loop. This is, I mean, my question, in fact, from you, because always I think that this is some kind of instability, so this loop should not work with low frequencies. And of course, there is a point here when we say low frequencies. What I'm talking is this frequency and that frequency are not same, by the way. Right? The input frequency itself is a signal. So we are not talking about that input frequency. Talking about frequency because frequency itself is a signal. So this input frequency comes like, for example, at the output of phase detector when you have a signal and now you can talk about the frequency. So low frequency means that when your input frequency doesn't change very frequently with time. It's a very low frequency. Means that variation, suppose you have 1 megahertz reference signal as an input. Therefore, that is almost constant with respect to time. So this means that low frequency region of this operation. You have an input frequency which doesn't change very fast with time. Therefore, frequency of variation of that frequency is very low. So that is that you have almost a constant frequency at the input, therefore loop settles in such a way that you don't have any input to the VCO. So charge pump eventually doesn't receive any signal. So this is my perception eventually, and if it is a filter, therefore still filter doesn't receive as such information because phase difference is 0. Otherwise, this loop should not remain. And of course, when you look at the loop, closed loop transfer function, you don't see any kind of frequency here. Because by adjusting the to omega n, you don't see any oscillation frequency. All frequencies okay. So this is something that usually is missed. Okay. Now coming to these new values. So if you remember in the previous case when we didn't have compensation, theta omega n was determined by the loop bandwidth, by the filter bandwidth, right? And these two have trade-off with each other. This is one thing. But here now, in this new transfer function, now zeta omega n is controlled by, eventually if we replace, because this is omega n square, I upon 2 pi k VCO is omega n square into C. So therefore, zeta omega n itself is omega n upon 1 upon RC. So now you have 2 degrees of freedom because it's the ratio of omega n upon 0. Yes, 2. So here we will. Now how will be location of this poles transfer function? So it has double pole at 0. Now if you increase zeta omega n, poles become imaginary. They will finally reach real axis. So this is sigma. And then we'll approach to 0. So this is the root locus for this system. So this is direction when you increase zeta omega. Or you can keep zeta omega n constant, only increase zeta. So there are different ways. But the point is that eventually that is correct, right? When you increase it, that you are increasing real. But you also, because zeta is by 2 upon 1 upon RC. So as you increase zeta omega n, right, to make it more stable, you are increasing ratio of omega n by 2 and 1 upon RC. Suppose, for example, you keep omega n constant. This means that you need to reduce 1 upon RC. That means that as you are increasing zeta omega n, 1 upon RC, all shifts to right, which is the limit when your zeta is infinite. So this means that though you are trying to stabilize the system, but at the same time you are reducing the bandwidth, which is good, of course, with respect to jitter and then noise performance, but it is not good with respect to latency of the loop. From other side, if you keep zeta omega n not very large, therefore you will have imaginary poles and therefore you will get better settling, but then you should be careful about the stability. That's why usually in PLL the best practice for design is to keep the Q of this transfer function to be some value between 0.5 and 3. These are usually values which are used in PLL design. So therefore your Q is not very high, is not very low. This means that your zeta eventually is not very high or very low. This is a very good practice for designing a PLL. So to give you an example, because now with this charge pump based PLL, we want to see that how we should look at the design constraint. So now, bandwidth of the filter, yes, bandwidth of the loop. Time constant eventually is, see, these arrows show poles, right? For example, suppose when a particular, if your zeta is 0, eventually you are here, right? When R is 0. Now when you move somewhere else, for example, you are here, these are your poles. Suppose you are reaching to real axis. So your dominant pole now by value which is closer to 0. The value which is closer is always dominant pole, which has minimum magnitude. See, this far from each other. Therefore, this pole as a dominant. And this bandwidth becomes closer and closer. You are reduced upon C. So what happens is that here I have not. This is the entire this diagram. Because at the same time your is less. See, zeta omega n eventually determines, fine. And then now here if you look, these poles are actually telling you what are the roots of that second order equation of which the time constant is determined. See, what is that zeta omega n? Zeta omega n is the real part of pole. And that is the reason we say that zeta omega n determines the bandwidth and the speed eventually. So zeta omega n is real part of the pole. When poles are real, so therefore now you will have new values, which is minus zeta omega n plus minus zeta omega n square, right? Minus omega 0 square. So when your zeta is greater than 1, you have real poles. And these real poles are splitted as you are increasing zeta. And this is a very common practice for second order systems. Now when you split these poles, what you are doing, you are increasing zeta to split the poles. For a given omega n, eventually you are increasing RC to do that. So means that, eventually means that you are trying to improve the bandwidth, to improve the stability, but at the same time you are reducing the bandwidth. So that's why a Q between 0.5 and 3 will be okay to handle this trade-off. So this is one thing. So for example, suppose if you choose Q equal to 0.5, example. So this means that Q is 1 upon 2 zeta. So this means that now your zeta is equal to 1. And therefore this means that your zeta omega n is same as omega n. And zeta is equal to 1. By the way, this is omega n square. Omega n square. So if you choose zeta equal to 1, which is Q equal to 0.5, this means that your resonance frequency of the loop will be 2 times of 0. 0 of the filter. And then if you look at this plot, crossover frequency, of course, is above 1 upon RC. So you crossover frequency, now knowing zeta is equal to 1, you can determine crossover frequency which may not be very far from omega 0. Now if you choose, for example, q equal to 3, then means that your zeta is equal to 1 upon 6. If you remember last example, in fact last to last example, zeta was 1 upon 20, which is too small. So zeta is equal to 1 upon 6, and therefore you will get this new relation. 3RC into omega n. So now your omega n is 1/3 of the 0. So now your omega n shifts to left. And your crossover frequency will be well above resonance frequency of the loop. But practically, I mean, values close to q.5 till q.1, q equal to 1, they are okay. I mean, I told you q equal to 3, but it's not always used. So therefore, what are now considerations in charge pump-based PLL? So in charge pump-based PLL, similar to first order filter that we had before, here also we have some trade-offs. Okay, so for first of all, one is determining I. I usually is determined based on the power dissipation. And you decide about the value of I, those current sources, based on the power dissipation. So this is something usually is given. So when I is not there, then what parameters remain for you? So eventually, therefore, still you are worried about two things. One is loop bandwidth, and one is loop settling time. Sometimes instead of settling time, people use phase margin. The same practice we have in op-amp design. So these two are same because phase margin and settling time are similar. So again, same trade-offs, but only now with new parameters. Okay. So for example, one relation also which is not very difficult to design, in fact obtain, I obtain it because then it helps you to have an idea how it is obtained. If you know, this was the loop gain, right? What I will do, I will replace it by crossover frequency. I will call this frequency omega CR. So CR is crossover frequency. And then I replace, I will make magnitude equal to 1. You will get an idea exactly how it will come. So you will get I, KVCO, here we have C also. One C is here. 2 pi C S square, therefore which will be omega crossover square into square root 1 plus R square C square omega square CR square equal to 1. So what I did, I just made magnitude of loop gain at crossover frequency to be equal to 1. We want to see what will be the crossover frequency, which is eventually close to the bandwidth of the loop. This is open loop gain. The crossover frequency of the open loop gain will be closed loop bandwidth of the loop almost, not exactly. So you make it equal to 1, therefore from here it will be this. So for example, I O upon 2 pi C. This is a term that is I is known, K VCO, but parameter is K VCO. I tell you, K VCO is usually not a design. You cannot force to design a VCO with a particular K VCO. VCO design is usually, we will have some examples of VCO. You may also have had it in other courses. VCO design, because we want to have a VCO. Designing a linear VCO for a particular range is not a kind of accept. Therefore, K VCO is not a design that designers should account on it. So that's why usually we don't open any account on K VCO. We assume K VCO is given to us. Therefore, if you notice in this relation, eventually the only parameters you have, that's why I call it like A upon C. A is a constant. This is a constant. The only parameter you have is C and omega C. Therefore, your crossover frequency is precisely determined by C and R. Therefore, this will be I upon I K VCO 2 pi was A, so this will be A upon C to square root 1 plus R square C square omega crossover frequency square equal to omega CR square. So this is the second order equation. Therefore, easily you can go of crossover frequency from this equation. So therefore, if you design about your crossover frequency, therefore this means that you know now the relation between R and C. And then if you choose Q of the filter, or eventually zeta omega n, according to this trade-off between stability and bandwidth, eventually you have RC omega n known, right? And omega n itself is a function of these two parameters. Because omega n square again is determined by the IKVCO upon 2 pi c. And because again here only c is a variable, therefore omega n eventually is, in fact, is actually omega n square. Therefore, eventually you have this relation. So eventually you have two relations and two variables which are R and C. You don't have a set choice. That is also a point in the design. Or loop gain also will be something like this is almost understood. And if you want to go with phase margin, instead of zeta, so phase margin is given by tan inverse RC omega crossover. Because you have only 1, 0, so it will be only this. But if it is the case, if you go with phase margin, if you go with Q, which is eventually similar thing, you will get that two equations and this. So omega CR is your choice. I is determined according to the limitations of power dissipation, and therefore, and then you decide about Q, therefore you can design. And usually this design is not a one-step design. You will design, you will simulate, and again you will come back, you will correct your design. So how, therefore now, and then by one more thing also I mentioned, if you would have chosen in such a way that you are here, you have a 0 and then you have 2 poles. So your pole will be before your 0. So therefore you will will see 0 and then pole. Therefore the kind of transfer function you will see will be a lead lag transfer function, because your 0 is absolute value of 0, magnitude of 0 is smaller than pole. Therefore you will have a lead lag kind of transfer function, and therefore you will see some kind of picking in the closed loop transfer function just because of this. If zeta is means that if zeta is large, it doesn't mean that you don't have picking. That picking is because you have a 0. Okay, so it's not because of Q. You may choose a larger zeta, like Q less than 0.5, but then you may see that picking. Then you don't think it is because of Q. You may wonder why it is like that. The reason is because your transfer has a 0. And then according to this root locus, your 0 appears first. Therefore, you will have some kind of picking. So your transfer function may look like this. If zeta is large, so you may get something like this. This is your 0. And then you will have pole, and there is another pole also. So you will get something like this. And the reason is you have a 0. But however, this is not good actually. This is not good, right? This is closed loop. Because suppose if you want to use this PLL as a demodulator, now at some particular frequency it has a different gain, and therefore you get nonlinearity. Easily it is a nonlinear demodulator. So these are some of the problems. Therefore that's why we usually don't go with a very high zeta. These are another problems with kind of transfer function. Okay, so these two, and okay, some of the effects tell you about non-idealities. Any question, any more about this part? I tell you about a little about non-idealities and then analog PLL. Okay. So in charge pump PLL there are several problems. So one problem is okay, so one problem is we have a charge pump. Okay, so this charge pump is a combination of two current sources connected to two switches, and then finally you will have another current source. So you have one source, one sink, and this goes to your RC. And these two are controlled by up and down. So how to implement? For example, just I tell you a simple implementation, very simple. Can be a cascade current source or can be a simple, so it doesn't matter. Suppose you use a simple implementation. Can be cascade. If it is cascade, you should add one more and then have bias, 2V bias. Then you have a switch. Naturally, because you have PMOS current source, you need a switch which should operate. This can be just as one switch, PMOS switch, or it can be a transmission analog switch in the form of a transmission gate, combination of both. And then one in MOS. So for example, you have V bias P, V bias N, and then you have up, you have down. But of course, if it is like that, this up and down won't work, because what you want is that when up is 1, you want this and sources the current. Therefore, you need to make this up bar to operate. So one of the problem is you have anyway, these are switches. So there will be parasitic capacitances between up and down. So therefore, you will see some kind of jump in the voltage when up and down are switched. Though we would expect this RC will take care of that, but the problem is that because now you have an R series with C, therefore those voltage across C doesn't change instantaneously, but voltage across R can change instantaneously. Therefore you will see some jump and again it will come back to a steady state. So these spikes are problematic. So that's why usually what people do is that they don't use a simple RC in charge pump. They add one more capacitor here to avoid this clock fit through, any kind of spike which are injected here. So this practically, of course, value of C2 is larger than C. And therefore now you have one more C. One more C means that now your filter, in fact your transfer function, which was second order, now it will be third order transfer function. But to take care of bandwidth, usually this C2 is chosen much larger than C. Not much larger means that say from 2 to 10 times in this range. So that you actually won't see the effect of C2 early. But it helps to reduce the effect of these spikes. So because now C2 will keep this voltage unchanged, and C2 but should be enough large compared to these parasitic capacitances of switches, so that it is same as a sample and hold circuit. It will keep the output voltage almost constant. And another problem is that because now you have up bar and down, therefore you have one inverter delay, for example, at least between up and up bar, but you don't have between down and down. Therefore that's why it's better to add a dummy switch, for example, or dummy kind of transmission gate, which will have same delay as one inverter. For example, this is always on. But you give up to this switch and then pass it to charge pump, so that now up and down will see same kind of delay. There won't be any problem. Otherwise, what will happen? Because there is a delay between up and upward. Suppose you have case up and down both should be high and therefore no current should be given. But this, because upward arrives late, therefore this still is not high, so it will remain low. This will go into low. Yeah, like this. For example, suppose I draw it. So suppose you have up, which should go from low to high, and then upward has some delay. And then, for example, down, which should also goes from low to high simultaneously, suppose. So now here what happens is that now, so if you look at this duration, so up is high, so therefore upward remains low and down is low. Therefore you will get some current, additional current that you don't expect to get. Source current, but you don't expect to have it. So during this duration, you will get additional I source because upward is low, so you will have some I source. But down is upward remains low. Okay, there is no I source. Okay, yeah, there is no I source because down is also 1. Yeah. What we want is that both of them are on. Okay, let's draw. So what will the problem, for example, here? Up is high. So upward is low. Therefore, there will be a source current, there will be a sink current, there will be no current, in fact, during this interval. Oh, upward will have, we should go low. Sorry, yeah, my diagram, I corrected. So suppose up, like this, then upward will be like this, then down, will be, for example, we want to be low, both are high, so no current should flow. So up is low, therefore upward is high, and then up goes high, so means that upward is low. So no current should flow. But still upward is high, therefore during this interval you will have current. And then you don't have any current. And then again here. Now again here upward is low, therefore, and down is low, therefore you will have one source. Okay, so therefore now to avoid these two problems, one is adding C2, one is adding a dummy transmission gate. Okay, what are other problems? Here I wanted to say impedance of C2 to be around, for example, 2 times to 10 times. I said C2. So impedance of C2. So C2, for example, can be, for example, half of C to 1/10 of C. Like half of C also is a little large. It's better to be less than. So for example, it's better to make it 1/4 at least. 1/2 is too small, too large. So these two will be added, and there are other few things also. Another problem is you may have actually mismatch between source and sink current. That is one of the big issues. So because anyway one is NMOS and one is PMOS, output impedance of these two are not same. And even if your output voltage level changes, so because output impedance is not always infinite, you will get some mismatch. And not only mismatch, but also this mismatch changes with Vout level. Because if Vout very high, I source will reduce. If Vout is low, I sink will reduce. So this mismatch between these two current actually is one of the main sources of error. So that's why like cascode with a high output impedance is definitely a right choice. And eventually what will happen is that now if you have this mismatch, eventually you will get some additional phase error that you don't have, but you will get, because these two are not matching each other. For example, simple case, suppose if everything has settled and then now there is no current which is given to this capacitor, right? But when it is not, it should not receive any current. For example, we had, for example, this case when you have a phase difference less than pi. So you will get some kind of waveform for up, and then down will be almost 0. So now when up is 0 and down also is 0, of course both of them are off. And then when up is 1, so you will receive some current. But then when reverse case, when down is up, down is 1. So for example, in other case after some time, so you don't receive the same sink that you will receiving during the source. Therefore, this keeps some charge unchanged on the capacitor. And this means that it is like that your phase difference is not same as before. In fact, the delta Q which remains quickly will be translated to charge, to phase difference, because we had, right, delta phi was the phase difference, and then you had I upon 2 pi. Right? This was in fact, phase detector transfer function. So exactly that delta Q will be translated to this delta phi. I upon 2 pi was the transfer function, right? For the phase detector. Yeah. I upon 2 pi. That was delta V. which is given to the filter. And this delta V is eventually given on to this filter. Now it has two more. So therefore, if you don't discharge same charge, because now the steady state, eventually C delta V will be your delta Q, which is C I upon 2 pi delta V. Phase difference. So the amount of delta Q which remains and doesn't discharge because of this mismatch will get translated to a phase error of delta phi. And value of this delta phi will be determined by this relation. In fact, delta phi will be 2 pi delta Q upon Ci. So this is called phase error, right? So this delta Q I'm talking about, maybe I call it delta Q dash. So this is not that common delta Q, this is that error we received because of charge which was on C and was supposed to get discharged by I think, but it didn't. Or even, for example, when both of them are equal and both of them are coming together, right? Means that up and down, both up bar is 0 and down is 1. So you expect with these two branches conduct same current, therefore there won't be any charge accumulation and reduction on C. This is also a steady state. But again, if these two are not same, there will be a continuous source or sink current, error current, which is giving charge, and actually this error will continue if loop stays in for a long time. But automatically it will lead to change in the frequency of the VCO. It will come back. But what will happen is that if you continue it for a long time, you will see that the frequency of oscillator is actually reducing and increasing. So you will see some kind of noise around the stable frequency. Suppose VCO was supposed to be stable at 10 megahertz, but now you see that there is something like a jitter kind of thing. It will reduce and again it will increase, reduce, increase. The reason is that because now this additional error is getting increased on the charge, on the capacitor, and therefore you will get an increase at the input voltage of VCO, frequency will increase. Now when frequency increases, therefore the loops tries again to return it back to the original frequency. Therefore it will discharge some charge now. Now your I sync will increase because now down will get activated. Now again frequency will come back. So this leads in fact to some kind of instability in the frequency, this phase error. So this phase error should be controlled by just using appropriate current sources. Another problem again exists here is that when you put always, this is a common problem, if you use a switch in the path of a current source, usually it is not a correct way of doing this. Or if you do, you should be very careful about to handle the current source when switch is off. Because as soon as this upper switch or lower switch are off, the current source cannot conduct. That means that your current source will be off. When current source is turned off, what will happen? Suppose you have a current source and this is your switch and this is load. And this is the current source and this is switch, which will be low or high. Now suppose this is high, therefore it will be off. So when it is off, what happens? So first of all, your output voltage is 0 practically, of course. Depends on what kind of load you have. If it is a capacitor, some constant value. Anyway, it remains at a constant value. What will happen for this node? This is a capacitor. This is connected to a parasitic capacitor. So this is C parasitic. Therefore, current source continues to charge that capacitor. So current source continues to operate. This capacitor getting charged, finally value of this capacitor, voltage which is on the capacitor, this slowly will rise and will approach VDD. As it approaches VDD, the current source enters into its ohmic region. Therefore, it won't be a current source anymore. And because it's not a current source, it will stop operating as a current source. And in fact, finally, even the current through this resistor will stop because this capacitor will charge to a VDD and then it will stop. So now you have a current source anymore. Now when this on, now you need to again bring the entire loop back to the original state and then turn this current source on. Happening. Therefore, beginning of any switching for this current, so these parasitic capacitors have been charged or completely discharged. So another issue would be because now their voltage is 0 or it is VDD. Eventually it's a very high voltage or a very low voltage compared to the scale we have. We have from 0 to VDD. Therefore now this switch is on at the beginning. Now you imagine what happens. So this is a C parasitic which is completely charged to VDD. And then you have had some output voltage here. So for example, this is 2 volt and VDD is 2 volt and your output voltage is, say for example, 0.8 volt. And now this switch is closed. So now you will have a charge redistribution between these two capacitors. Because your current source doesn't operate as a current source right from the beginning. Therefore, this creates again a lot of error on the voltage which was stored over here. And this leads again to phase error. And phase error always means that the frequency of the loop takes more time than you expect to reach to its final value. And therefore, to avoid it, it is better to keep these current sources on. When they are always on, so it won't, at least problem will be less. I'm not saying that problem will be omitted, but at least it will be less. But how to do that? You need to provide another path for current to flow when these switches are off. That's why usually 2 additional dummy paths are provided which are exactly opposite to this path. And they are getting on only when, for example, for upper path. Now what you can do is that you add one more path. Right? And for example, put a switch over here. And even if you want to exactly mimic similar things, so it's better you keep this voltage almost similar to the voltage you expect to observe here, but it's not practically possible because this voltage is not constant. But you can put a resistor, for example, to ground, and now this will be exactly opposite to this. For example, if it is up bar, this will be up. So now when up is low, so that will help this current source to continue feeding the current, and therefore current source won't turn off. And because the current source doesn't turn off, therefore the voltage at this node doesn't go to reach to VDD, and the problems are less. But it's not like that, it is completely omitted, because anyway the voltage here may change compared to the voltage you had previously. So similarly, you can provide same path for down. And then a little bit about jitter. So what is jitter? Jitter, you know, of course, how now in PLL jitter comes to the picture. Anyway, you have a VCO. If you don't have anything, at least you have a VCO in the loop. Therefore, that means you have a jitter, because when you have an oscillator, it is impossible to give you a constant frequency at the output. Because VCO has its own noise, internal noise, devices have its own internal noise. Therefore, operating point of VCO is not a constant operating point. And when operating point changes because of noise, therefore oscillation frequency changes. Simple. Though you may say that, okay, there are LC, suppose you have an LC tank VCO and all these precautions, but still even in an LC tank VCO, because you have, for example, flicker noise of the devices, that flicker noise may change the bias current. Changing the bias current changes the Q, and therefore it's not like that always only, and even it changes the amount of current which is fed to your tank. So therefore it's not like that always it will keep everything constant. So you will have fluctuation around some center frequency. So eventually that means that you expect to have only a single frequency, but actually you will see more than one frequency. And the reason is because even your tank is not a pure tank. It is fed by the current which is coming from the transistor. And then if the current changes, therefore effective output impedance changes. And therefore effective Q that you observe changes. And when effective Q changes means effective bandwidth of the oscillator changes. Some frequencies again come and go. So means that always if you look at the spectrum, you won't see a single peak. You will see a peak and then you got some kind of stretched spectrum around center frequency or oscillation frequency, which is because of this jitter. And there are, of course, random noise and other issues. So, and of course, you have a frequency which is also applied to the loop from outside. That source also again has its own unstable frequency. Therefore, overall, this is jitter exists everywhere. Now, suppose if you have, therefore, we can two kind of jitter. One is jitter at the input, and one is VCO jitter. So how to show it? Because jitter eventually is variation of the frequency, and therefore jitter eventually is the phase noise. So the noise that you observe on the phase, you can convert it in this way, because if your phase is constant, or if your phase is the phase that you expect, for example, linearly changes with the time. So this is phase you expected, and that is correct for a single constant frequency. But if you have some kind of random variation of this phase, then you can just add it to your phase. That's why the best way to model it, for example, if you have input jitter, this is your phi in, right? You just add your phase noise over here. That's enough. And then here you have I show VCO because VCO generates noise. Again for VCO, you add one phase here. So therefore, here this is phi n in. And Feed it back. Okay, to make it phase, put on this. If you look at the transfer function of the system with respect to input phase noise, it's same as phi in, right? Phi in, because they are just added. So it's same as before. That we know. Right? And therefore, bandwidth of the loop with respect to input noise, phase noise, is determined by the bandwidth of the loop that we had before for V out or for phi out. So same consideration means that bandwidth should be low enough to avoid any kind of jitter and phase noise. So we should be aware of this. And but if it is at the phase noise side, that is VCO side, then now your input is here. Therefore, to make get the transfer function, you make phi in equal to phi n in equal to 0, and then get the transfer function with respect to phase noise of VCO. Therefore, phi out is with respect phi n VCO. This transfer function is different. So, for example, for the charge pump, it was I upon 2 pi R plus 1 upon SC. So, we replace. So, now these two are removed, and this is your input. So, it is like that. These two are in your feedback loop now. Yeah. If I remove these two, so this is feed forward. Yeah, it means phi n directly comes to phi out. Right? This is your feed forward path, and this loop is your feedback path. Therefore, your feed forward path now is 1, and then you have one feedback, which is I upon 2 pi R plus 1 upon SC into K VCO by S. Now, interestingly, if you look at this transfer function, if I simplify, it will be this. Very interesting. That's a high pass oh, sorry. I missed time today. So it's a high pass transfer function. So for phase noise of VCO, loop transfer function is high pass.